Welcome to another exciting calculus video. We're going to be looking at section 3.5, a summary of curve sketching. The homework for this section is a handout. I think there's 2 or 3 graphs on it. And then these 3 are from the textbook, page 254, analyzing the graphs of the first and second derivatives. Those will be like the last couple examples here in the video. And the book says, 3.5, Summary of Curve Sketching. It would be difficult to overstate the importance of using graphs in maths. Well, I guess you can read this for yourself. You can pause the video and check it out. But here we got a list that says, so far we've studied concepts that are useful to analyze the graph of a function. And some of this stuff is even non-calculated, like x and y intercepts. We can find those without calculus. The symmetry of a graph, we talked about that in pre-calc. Same thing with domains and ranges, the inputs and the outputs. The continuity of a function, that was more here in calculus. We talked about continuity. Vertical asymptotes, we saw those in college algebra and pre-calc. Horizontal asymptotes, we found more here in calculus. End behavior, infinite limits at infinity. And then the real calc stuff, derivatives, relative extrema, the mins and the maxes, the concavity, and the points of inflection when that concavity changes. So it says when you're sketching the graph of a function, either by hand, blah, blah, blah. Yeah, this isn't overly critical either. Okay. They got some guidelines here to analyze the graph of a function. Step 1, determine the domain and range of the function. This is especially important if you've got a radical in there. Remember, no negatives under radicals. Domain also, watch out for the vertical asymptotes, the numbers that are going to zero out your denominator in the original function. 2, determine the intercepts, x and y, any asymptotes, vertical, horizontal, or even slanted. And the symmetry of the graph can help figure out what's going on also. Third step, locate the x values for which the first derivative and the second derivative are 0 or non-existent, and use those results to determine the extrema and the points of inflection. And then it says here, in these guidelines, note the importance of all the algebra, as well as the calculus, to solve equations. When you're setting your function equal to 0, that's going to be algebra. First derivative equal to 0, more algebra. Second derivative equal to 0, even more algebra. The hardest thing about calculus is all the algebra. Okay, here's our first function to check out the graph of. We've got this rational function, and in this part of the book, we've done enough of deriving. So here, the book just hands us the first and the second derivatives. And these would be derived with the quotient rule. Notice the denominators, x squared minus 1, x squared minus 4 quantity squared, x squared minus 4 quantity cubed, because we're using the quotient rule to get those, so the denominator doesn't change much. Down here below, we've got some key parts we're going to get from looking at f and f prime and f double prime. We will come up with a table here that give characteristics of the graph, and then we'll start working on the, I didn't want to spoil that. I need the graph of the function. I need a blank piece of graph paper. And there's the graph we'll put together as we go along. All right. So let's start filling in some of this stuff. X-intercepts, that is where f of x is equal to 0. And if it's in the form of a fraction, it's where the numerator alone is equal to 0. If we set that equal to 0, we'll get plus or minus 3. X-intercepts, plus or minus 3. Y-intercept, remember that is f of 0. Put a 0 in there and see what comes out. Well, the numerator will be a negative 18. Denominator will be a negative 4. Negative 18 over negative 4 is positive 9 halves, or 4.5. So there's our x and our y intercepts. Let's even put those in on the graph right now. Plus and minus 3 on the x. And then 4.5 on the y. So there's some interesting parts of our graph. Vertical asymptotes, that is when our denominator is equal to 0. So x squared minus 4 equals 0 means x will be plus or minus 2. X equals plus minus 2 are the verticals. Let me even go to my graph. Got a vertical here, positive 2. Another one here at negative 2. Oops, what am I doing? There we are. Horizontal asymptote. Remember, that's the power struggle between the numerator and the denominator. If we distribute the 2, we're going to have a 2x squared. Our denominator is x squared. So if it's a tie, remember we use the leading coefficient fraction. So that's y equals 2 is our horizontal asymptote. So the graph is really coming together. A critical number. Now it's time to actually go to the derivative. Remember, we find critical numbers by setting f prime equal to 0, or where f prime fails to exist. Well, here's f prime. If I set the numerator equal to 0, I get x is 0. And if I set the denominator equal to 0, I get the same plus and minus 2. Ooh, well, hold on. Critical number is where the derivative is equal to 0. Oh, yeah, well, and the plus and minus 2 also. Next up, possible points of inflection. Well, that is when we set the second derivative equal to 0. So here's my second derivative. If I set this equal to 0 or just the numerator equal to 0, and I start solving it, I'm going to get x is the square root of a negative 4. Or, the square root of a negative 4. So here, possible points of inflection, there are none. No points of inflection. Domain. Remember, look for radicals and denominators. I see no radical, so we don't have to worry about a negative under there. But our denominator would zero out. We've already established this. X cannot equal plus or minus 2. We're not allowed to use those numbers. They're not in the domain. They would zero out our denominator. Symmetry, if we're not sure about the symmetry, it's not critical to getting down a good graph. Our test intervals are going to come from the critical numbers, and the asymptotes are going to chop everything up. So our critical numbers are 0 and plus and minus 2. 0, 2, and negative 2, and plus and minus 2 are also where the vertical asymptotes are. So those are the numbers that are going to chop us up, 0, 2, and negative 2. Now watch this. I'm going to go from negative infinity to negative 2, and then leave a space there, negative 2 to 0, 0 to positive 2, and then 2 to infinity. There's the intervals like we've been checking for a while now. But we're also going to do the exact value. X equals exactly negative 2. X is exactly 0. X is exactly 2. Now here, f of x, we're only going to do that at those x numbers. For f prime and f double prime, we'll be checking the intervals. Because we don't want to check just any arbitrary number in the original function. It's just going to give us some point. Let's go back up here and look at these again. Notice here this denominator in the first derivative, f prime, that's a quantity squared. That is always going to be positive no matter what. Okay, let's start filling some stuff in. First interval, negative 2 to negative infinity, I'm going to use a negative 10. If I put negative 10 into the first derivative, my numerator is going to be a negative 200. We've established denominator is always positive, so our first derivative is negative. And if it's negative, that means the function is decreasing. If I put the same negative 10 into the second derivative, we're going to have here in the parenthesis negative 10 squared is 100, times 3 is 300, plus 4 is 304, but that gets multiplied by a negative 20, so our numerator is negative. Denominator, put a negative 10 in there, we square it, get 100. 100 minus 4 is positive, and if you cube that, it is positive. Negative over positive is a negative second derivative, so we are concave down. Negative and concave down. And let's even, I wonder if we can do that on the graph right now. Negative infinity to negative 2, it is decreasing and concave down. Here is negative infinity to negative 2, and our graph is going to be going downhill, and it is concave down. And we've got an x-intercept, and we've got to obey the asymptote. And I didn't like that one there. There we go, that's a little better. So there's our first interval from negative infinity to the asymptote. Our next interval will go from negative 2 to 0. Let's see what happens in there. Oop, but first, we've got to put in exactly negative 2. If we put negative 2 in the original, it's undefined. If we put it in the first derivative, undefined. Second derivative, undefined, and that is because we have a vertical asymptote there. And let's go down to x is 2 and do the same thing. Undefined, 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 v, a. Okay, interval time. And let me erase this. There we go. Next interval, -2 to 0. So we're going to use x equals -1. If I put -1 in the numerator here in the first derivative, 20 times -1 is negative. We've established the denominator is always positive. So that is a negative first derivative, and our function is decreasing. And if we put -1 into the second derivative, our numerator is this quantity here, and that's going to be 3 plus 4 is 7 times -20 is a negative numerator, negative. Down here, -1 squared is 1, 1 minus 4 is negative, and when you cube that, it is also negative. Negative divided by negative is positive, and that part of the graph is concave up. So here we have a negative first derivative, so we are decreasing and yet concave up. Decreasing, but concave up, so it would look like that. Okay. Now our next interval from 0 to 2, or actually we're going to put exactly 0 in. If we put 0 in, we've already done this, that is our y-intercept of 9/2. If we put 0 into the first derivative, we get 0 over 16. So the first derivative is equal to 0, and that makes sense because that's how we found that number. We set the derivative to 0. And if I put 0 into the second derivative, let me clear this out. If we put 0 into the second derivative, we're going to have 0 plus 4 times a -20. That's a negative numerator. And our denominator, 0 squared minus 4, is negative, and you cube that, you get a negative. Negative divided by negative is positive. If it's positive, remember it's concave up. And this is a critical number. If we put a critical number into the second derivative and it's concave up, we know that that is a min. So when we come over here, we know this is going to be a min, so we can sort of finish the graph off like this. But let's check that interval from 0 to 2. Oops. From 0 to 2, I'm going to put in a +1. So now my derivative numerator is positive over the positive denominator. That's a positive first derivative. And the function is increasing. And if we put the 1 into the second derivative, we're going to get the same negative over negative, which is positive. And that is con up. So increasing and con up, and we've already sort of filled in that part of the graph, and that makes sense. Increasing and concave up. Okay, we're getting close. 2 to infinity, I'm going to use +10. So if I put a 10 in here, that's positive over positive. We are positive first derivative and increasing. And if I put the +10 into the second derivative, my numerator is going to be, negative, a negative numerator. And then down here, I'm going to have 10 minus 4, that's positive. Cubed is also positive. Negative over positive is negative. And we are now concave down. So let's see this last interval, increasing and concave down as we go to the left. So here I'll start down here, and we are increasing and concave down, and we've crossed our x-intercept, and we're obeying our asymptotes. So there's our graph. Pretty good job for using our new little bits of info from calculus. So here's the book's version of it. They got the vertical asymptotes, the horizontal at 2, and we've got our min at 0,9/2. Looks like a good graph. Example 2, kind of similar. There's going to be a few differences in this one, though, as we go through. And once again, they do give us the first and second derivative in a nice factored form. Here's our original function, f of x, and here's our first and second derivatives. And I wonder if I can make this, yeah, maybe I'll put this over here so I can make it a little bit bigger. Okay, up first, the x-intercepts come from the original function. Set the numerator equal to 0. And when you look at that numerator, okay, I'm going to try to factor it. Factors of 4 add up to -2. It doesn't work. So I'm going to check my discriminant, b squared minus 4ac. Remember, if this is negative, you have no x-intercepts. Well, they're imaginary, but you don't have any real ones. So b squared would be 4 minus 4ac. A times c would also be 4. So that's 4 minus 16. So we have a negative discriminant, and that means no x-intercepts. So we're not going to cross the x-axis at all. Up next, the y-intercept. That is f of 0. So if I put zeros in for all the x's, I'm left with 4 over -2. And that is y-intercept -2. Vertical asymptote. Remember, set the original function denominator to 0, x minus 2. So that just gives us x equals 2. Horizontal asymptote. Remember the power struggle. Here the numerator is more powerful, so there is no horizontal. But what if I scratch that out and make it vertical? Or, excuse me, slanted. Slant asymptotes. So we're going to do a little long division to get that slant. I'm going to come down here, a little room for scratch work. X minus 2, we're going to divide that into x squared minus 2x plus 4. My first thing up top would be an x, and when I multiply, that's an x squared minus 2x. And we subtract, those are zeros. We bring down the 4, so that is our remainder. X plus 4 over x minus 2. Remember, though, these the remainders don't mean anything for slant asymptotes, because we're going to let x get infinitely large, so that remainder heads toward a 0. So our slant asymptote is just y equals 1x plus 0. All right. End behavior. So the end behavior, remember that's driven by the first terms. X squared divided by x is just x. So it's going to behave just like our slant asymptote. As x heads to infinity, y heads to infinity. As x heads to negative infinity, y is also heading to negative infinity. Okay, time for the first derivative. Critical numbers is where the first derivative is equal to 0 or non-existent. So critical numbers, 0 and 4. 0 and 4. So set that x equal to 0, set the x minus 4 equal to 0, and we get 4. Now the denominator would be zeroed out at 2, but remember those aren't going to be mins or maxes. Those are where we already have our vertical asymptote set up. Or excuse me, at positive 2, we're going to have a vertical asymptote, so that can't be a min or a max. Possible points of inflection come from the second derivative right here. So if I set the numerator equal to 0, I just get 8 equals 0, and there is no place to even put an x in there. So point of inflection, none. The domain, remember to look for radicals and division by 0. There are no radicals, so we've just got to exclude x equals 2. The set of all x such that x does not equal 2. Now the intervals are chopped up by the critical numbers and the asymptotes. So we had critical numbers at 0 and 4, an asymptote at 2. So 0, 2, and 4 are going to be the numbers to determine our intervals. 0, 2, and 4. So we're going to go negative infinity to 0, 0 to 2, 2 to 4, 4 to infinity. And of course, we're going to check exactly what's going on, exactly at 0, exactly at 2, and exactly at 4. And here are the original function as well as the first and second derivative. So I just feel like let's go through and do the actual points first. I'll stick with my red ink. If we put 0 into the original function, out pops -2. That is our y-intercept. If I put -2 into the first derivative, we're going to get, 0. We're putting 0 in there. We're going to get 0 in the numerator. And then our denominator is going to be a negative 2 squared or 4, so that is just 0. And if we put 0 into the second derivative, 0 into the second derivative, we have a positive numerator, and 0 down there will be a negative 2 cubed. That's negative. Positive over negative is negative. And if we have a negative value there, that is then concave down. Con down. Let's go to x equals 2. Notice in the original and the first derivative and the second derivative that 2 zeroes out all those denominators. And we know that is undefined, undefined, undefined. Oops, I'm writing that in the wrong spot. Oops. Undefined at all of the 2's because we have a vertical asymptote. Okay, let's put 4 into the original function. You put a 4 in there, out pops a 6. So that's a point we can graph when we get to the graphing part. If we put 4 into the derivative, this part here is going to zero out, so that zeroes out the numerator and gives us an overall value of 0. And if we put 4 into the second derivative, we have a positive 8 in the numerator. 4 minus 2 is a positive number cubed, which is still positive. Positive over positive is positive. And we are concave up. Okay, now let's start doing our intervals. Negative infinity to 0, so we can't use 0, but we can use my favorite, x equals negative 10. And if I put, remember now here, this denominator is a quantity squared. It's always positive. And if I put negative 10 in the numerator, I'm going to have a negative 10 times another negative number. That is positive. Positive over positive is positive. And that means our function is increasing. Let's put the negative 10 in this second derivative. Our numerator is a positive 8. And then we're going to have negative 10 minus 2. That's negative. And when we cube it, it stays negative. Positive over negative is negative. Negative. And that means we are con down. Okay, 0 to 2. Infinitely many numbers in there to choose from, so 0 to 2. Let's do x is 1. If I put 1 into the first derivative, I'm going to have a positive 1 times a negative 3. That's a negative numerator. Our denominator is quantity squared. That's always positive. So that gives us a negative value overall, and our function is decreasing on the interval. The second derivative, if we put a 1 in there, we're going to have a positive 8 in the numerator. 1 minus 2 is negative, and we cube that, and it's also negative. Positive over negative is negative, and we are concave down. Let's hop over to the graph and do a couple of these, I think. Well, no, hold on. Let's save that to the end. Let's save it till the end. 2 to 4. So let's use x is 3. If I put 3 here, that's a positive 3 times 3 minus 4 is negative. So that's a negative numerator. 3 minus 2 is positive, and we're going to square that, and it's going to stay positive. So that is negative over positive is negative, and our function is decreasing. Let's put that 3 in the second derivative. 8 is our positive numerator. 3 minus 2 is positive, and we cube that, and it stays positive. Positive over positive is positive, and we are concave up. Last interval, 4 to infinity. We'll use my favorite 10 in there. So that's 10 times 10 minus 4. That's positive. 10 minus 2 quantity squared is positive, so our value is positive, and the function is increasing on the interval. And then our second derivative, numerator 8 is positive, 10 minus 2 is positive, and we cube that, and it stays positive. So that's also positive and concave up. Okay, let's put our graph together. Let's start with our x and y intercept and our asymptotes. We had no x-intercepts. We crossed y at negative 2. We also did come up with the point 4, 6 right here. 4, 6 is a point. So 4, 6. We have a vertical asymptote at 2. Whoa, whoa. Vertical asymptote at 2. There we go. Our slant was y equals 1x plus 0. So we're going to go through 0. Slope of 1. It's going to look like that. Okay. The graph's really coming together. So our first interval, negative infinity to 0, we were increasing and concave down. So increasing and concave down. So we got to the y-axis, or 0. And our next interval is 0 to 2. 0 to 2, 0 to 2, we were decreasing and concave down. So we've hit this point. Now we are decreasing and concave down. And note here that 0 was a critical number. 0 was a critical number. So if it is a critical number concave down, that means that 0 is a max. And we see that now on the graph. This is the max. Our first derivative critical number went into the second derivative. It was negative, so it's concave down. That means we have a max. Okay, our next interval is 2 to 4. So in between here, 2 to 4. From 2 to 4, we were decreasing and concave up. So we decreased and concave up, mind the vertical asymptote. And now our last interval is 4 to infinity. Oops, wrong way. 4 to infinity, increasing, concave up. Increasing, concave up. Oops. And we did have 4 was a critical number, and when we put 4 into the second derivative, 4 went into the second derivative, it was positive, concave up. If it's concave up, that critical number must be a min. So there we know that now is a minimum value. And the graph is done. Looks pretty good. What's next? Another one. This one's not a rational expression, just a polynomial. So we've got, there's our original function. Here are the first and second derivatives in factored form. Now let's, the first one, f of x, that can also be put into a factored form. That is x times x minus 4 quantity cubed. There we go. So there's f of x and the first and the second derivatives. And let me do this. Oops. Okay. All right, x-intercepts. Here's our original function factored. Set the first factor to 0, and you get x is 0. And in the parenthesis, you're going to get x is 4. Okay. Y-intercept. If we let all the x's go to zeros, we'll get 0 times negative 4 cubed, which is y equals 0. So we've got the origin, and x is 4 as a couple of points. Vertical asymptotes, there is no denominator to 0 out, so there are none. Horizontal asymptotes, remember that is our the power struggle between numerator and denominator. There is no numerator denominator, so there are none of those. End behavior, remember x to the 4th. So on a graph, it's sort of going to look like this, up to the left, up to the right. So as x approaches plus or minus infinity, y is approaching positive infinity. So there's our end behavior. Okay, calculus time. Critical number comes from the first derivative equal to 0, which I just underlined here in blue. If I set the first set of parentheses to 0, I get 1. And the second set of parentheses to 0, I get a 4. So there's a couple of critical numbers there. We will use those to chop up our intervals. As well as, well, possible point of inflection. If we set the second derivative equal to 0, we're going to get x is 4 and x is 2. X equals 2, x equals 4. So this point x is 4, it could be a critical number, it might be a point of inflection, hey, maybe it's even nothing. We'll find out as the problem continues. Domain, there are no radicals, there are no denominators, so this is all real numbers. The test intervals will come from our critical numbers. So it looks like what, 1, 2, and 4. Yeah, 1, 2 are possible points of inflection, are critical numbers. 1, 2, and 4 are going to chop up our intervals. So let's see here. 1, 2, and 4, negative infinity to 1, 1 to 2, 2 to 4, and 4 to infinity. And as always, we will check the exact values at 1, and at 2, and at 4. Okay. And here are the original function and the two derivatives in their factored forms to make our job a little easier. So let's look at our first interval. Negative infinity to 1. A good number in there to use is 0. Again, with the intervals, we're not going to do f of x. But the derivative, if I put 0 in there, this is going to be a negative value. And this is going to be a negative, but it's squared. So that's negative times positive. That is negative. And our function is decreasing on the interval. And if we put 0 here into the second derivative, 0 minus 4 is negative, 0 minus 2 is negative. Those are going to multiply to a positive, and we are concave up. At exactly 1, if you put 1 into the original function, you're going to get negative 27 pop out of there. Negative 27. And if we put 1 into the first derivative, we're going to get a 0, because that's how we found it, by setting our derivative equal to 0. And if we put 0 into, or no, x equals 1 into the second derivative, we're going to get 1 minus 4 times 1 minus 2. That's negative times negative. That's positive. That means it is concave up. Con up. Okay, next interval, 1 to 2. I guess we're kind of stuck in there with 1.5 or 1.5. 1.5. If I put that here into the first derivative, I'm underlining in blue, that's going to be 1.5 minus 1, that's positive, times this quantity squared, that's positive. Those are going to multiply to a positive, and our function is increasing. And if we put 1.5 here into this second derivative, I'm underlining in red, 1.5 minus 4 is negative. 1.5 minus 2 is negative. Those are going to multiply to a positive. And we are con up. Okay, now this the critical number at 1. Yeah, 1 was a critical number, and when we put the first derivative critical number into the second derivative, it's positive. That's con up. So we know that point is a min. We know that 1 comma negative 27 is a minimum value. All right, exactly 2. If we put 2 into the original function, we're going to get out of there a negative 16. And if we put 2, let me get rid of some of this down here. If we put 2 into the first derivative, 2 minus 1 is positive. The second term is always positive, so that's going to be positive and increasing function. And let's put that 2 down here in the second derivative. 2 minus 4 is negative, but this 2 minus 2 is 0. So that's equal to 0, and that is a possible point of inflection. Possible POI. We'll figure out in a minute if it's really a point of inflection. All right, next interval. 2 to 4, let's use x equals 3. If I put 3 here, 3 minus 1 is positive. This is quantity squared, it's positive. So those multiply to a positive, and our function is increasing. And if I put a 3 in the second derivative, 3 minus 4 is negative, times 3 minus 2 is positive. Those are going to multiply to a negative, and we are now concave down, con down. Now, if you look here, we were con up, and then con down on the other side. So what we thought was a possible point of inflection is now assuredly a point of inflection. So we can cross out the possible part, because the concavity did change. All right, next number up, x is 4. If we put 4 into the original function, we get a 0. If we put 4 into the derivative, it zeroes out this term, that's a 0. If we put 4 into the second derivative, it'll zero out that term and zero out the whole thing. So that doesn't tell us too much there. Let's see. Remember, this is a possible point of inflection. It's a possible min or max. Let's see what happens. If we get an increase to decrease change, it could be a min or a max. If we get a concavity change, it is a point of inflection. So 4 to infinity, let's use x equals 10. If I put 10 in here, 10 minus 1 is positive, times a quantity squared is positive, so that is positive and increasing. So it's not a point or a min or a max because we increase to increase, so it's neither of those. And if I put 10 into the second derivative, 10 minus 4 times 10 minus 2, that's positive times positive. Those are both positive, so we are now con up. Con up. Here where it was con up, a little bit ago it was con down, so this up here is a point of inflection. Okay, let's put together a graph, come up with a few of our points from the table. We did have the point, our x-intercepts were 0 and 4. So 0 and 4 are x-intercepts. We had this point, 1 comma negative 27, so over 1 down to negative 27 about here. And on that interval, we were decreasing, but concave up. And then from 1 to 2, we were increasing con up. Ooh, here's another point, 2 comma negative 16. So over to 2, negative 16 would be down to about here. Okay, now we can start to put this together. Notice that this was, we had a min at 1, negative 27. So this point down here is a min, and it'll look like this. So we came in decreasing and concave up. And then after this point, we were increasing but concave down. So it would sort of like that. Increasing, concave down. Oops. Ooh, no, I read that wrong. That's increasing concave up. From 1 to 2, increasing concave up. So it's going to look more like this. That curvature is going to be reversed. Increasing but concave up. And then from 2 to 4, oops, wrong way. 2 to 4, we're increasing but now concave down. So we're still increasing, but the concavity changes to down like that. And then from 4 to infinity, we're increasing and concave up. So it's going to change like that. And there's our, again, this is a point of inflection. We saw the concavity change. Also here at 4, con down to con up, we had a concavity change. We found this min at 1, negative 27. Okay. Okay. That's it for the graphing ones. Now, these last two are just analysis of first derivative and analysis of second derivative. These can be tricky. They're kind of hard to wrap your head around sometimes. Example 9, we have a first derivative graph, and I sort of blew it up here, made it a little bit bigger, and I sort of highlighted some stuff. When I first tackled these, I made sure to point out to myself which parts of the graph were above the x-axis, so I highlighted that in red. So the first derivative is positive. What do you know about positive first derivatives? It means you're increasing on the original function. I used blue ink to denote where the graph was under the x-axis here. So the first derivative is negative because that's below the x-axis. I also put some points where the first derivative is exactly equal to 0. So here at, what would that be, negative 6. This here would be negative 3. And this looks like at positive 3, we have where that would equal 0. So when we determine our intervals, these are going to be our key points. Again, we got here negative 6. Negative 3, positive 3. So let's go back here. Interval, negative 8. Oop, I don't like that green ink. And notice here we are just negative 8 to 8, so there's no infinity in here. So negative 8 to negative 6, negative 6 to negative 3, negative 3 to 3, and 3 to 8. So it says here, what is the sign of our first derivative? So if we're above the x-axis, well, let's do a part where we're below. Here, from negative 8 to negative 3, we are below. So negative, negative 8 to negative 6. Negative 8 to negative 6, that is negative. And then the rest of the graph is above the x-axis. So I'm going to highlight this part in green. So from negative 6 to positive 3, we're above. So this is positive. and then this is also positive, and that is one big interval. Now notice here we didn't go below the x-axis, but we did hit it. For one moment we were exactly 0, but now we're back up above, so here is another interval. That would be its own separate interval. So to answer part A, on which intervals is the original function f increasing? That is when the derivative is positive. So for part A, we could say from -6 to 3, that's one big interval, and then also from 3 to 8. Notice the parenthesis because 3 is not included in that answer. Okay. Okay, part B might be, in my opinion, maybe the trickier part of this one. On which intervals is the original graph concave down? So what do we know about the second derivative? If it's concave down, the second derivative is going to be negative. What does that look like on our first derivative graph? Well, the second derivative is negative where this graph is sloped downward. So I'm just going to use black ink and highlight, okay, here's where at the top of a hill, here's the bottom of a valley, here's where the graph is going down. So this is where f prime is decreasing or negative. That's going to make our second derivative would have a negative slope on that same interval. So this would be from -3 to 3. So part B, -3 to 3 is where that the graph of the original is concave down. Ooh, and I guess we should have filled in this last column or row here on this. What is the graph of f prime doing? So from -8 to -6, here it is increasing. From -6 to -3, it is staying increasing. And now here from -3 to 3, we are decreasing. And then from that 3 to 8, we are back to increasing. So part B, we can see right here. When it is positive and decreasing, when the first derivative is positive and decreasing, we are going to have concave down. Okay, now part C. At what x value or values does the original function have a relative extrema? Well, what do we know about relative extrema? It's when the first derivative changes from increasing to decreasing or decreasing to increasing. So f prime must go from increase to decrease, or it could go from decrease to increase. Those could be mins or maxes. What does that look like on the graph? Well, remember, increasing is positive, decreasing is negative. So we're going to have an extrema when our f prime, when our derivative graph crosses the x-axis. The direction it crosses will determine if it's a min or a max. Let me go to my blown up graph. So here is -3. To the left of that, our f prime was negative, so it was decreasing, and then we hit 3, and now we are increasing on the other side. As soon as we cross 3, now we're up here positive, so on the other side, our function is increasing. Decreasing to increasing means we have a min at -3. So for part C, x equals -3. What am I doing? X equals -3. Now, they didn't ask us if it was a min or a max, but in this case, we went from decreasing to increase. It would be a min. Now, look at here. Here, we hit the x-axis, but we did not cross it. To the left, f prime is positive, function's increasing. On the other side, it's still positive, increasing. So if you go from increasing to increasing, it's not a min or a max. It's neither. Okay, and the last one, at what x value or values does the original function have a point of inflection? Well, remember, f double prime equal to 0 gives you a possible point of inflection. Here is our graph of f prime. Where would f prime have a horizontal tangent line? Well, it would have one here. So this is where our second derivative would be 0 at -3. And it would also have a horizontal tangent line here at +3. So for part D, x equals +3, x equals -3. Okay, so there's a first derivative graph, and we can analyze things about the original function. Our last example here is example 10, we have a graph of a second derivative. So we've got a couple things here they're asking us based on this second derivative graph. And again, I did blow this one up. Why, oh, there it is. The red parts are where f double prime is positive. The blue parts are obviously where it is negative. So here it says, I'm going to move this up here a little bit, make this a little bit bigger. On what intervals is the graph concave down? And on what intervals is the original function f prime, the original function's first derivative, increasing? So let's check out our table here below. So here when they're talking concavity, remember that second derivative positive or negative. So our intervals are just going to be where we're above or below the x-axis. So here would be -1 and -2. And here's +1 and +2. So those are going to be our numbers that chop up our intervals. And here we're going to go -∞ to -2, -2 to -1, -1 to 1, 1 to 2, and 2 to infinity. And this next row is pretty simple. What is the sign of the second derivative? Well, the blue parts are where it's negative. So that's -2 to -1 and 1 to 2. 1 to 2, it's negative. -1 to -2, it's negative. But the rest of the graph is above the x-axis. So that's where it's all positive. Positive. So that is going to help us answer part A. On what intervals is the graph concave down? Concave down means second derivative negative. Our second derivative is negative from -2 to -1 and from 1 to 2. Yep, that's it. Now for me, it's this part B. Originally, it was the hardest to wrap my head around. And this might be the most concise way to say it. They're asking, when is f prime increasing? F prime is increasing when the original f of x is concave up. Concave up. So if we know where the original graph is con up, that is where f prime is increasing. And here's where it's concave up when the second derivative is positive. So the interval -∞ to -2, -1 to 1, and 2 to infinity is where our f prime would be increasing on the upward trend. Okay, that is the last example, I believe. We'll do some of these odd problems in class. Okay, that should do it. I hope you enjoyed the video.